I had to pick up my presentation from my office computer, but some VPN issue. Anyway, would you please let me know? Would you please let me know what time how many minutes I have, so that I can accordingly budget my time? I think I need to conclude it in about now 25 minutes. Am I right? 25 minutes.
Yes, sir. Yes.
So I would have so what I'm going to do, I'm just going to go through some of the key highlights of my presentation. May not go through all my slides, but I think I'll provide enough of information that there leave some time for question answers later on.
Sure, sir. Thank you, sir. You can start.
Thank you. I'm just going to start sharing my screen. I'll just share my screen. Are you able to see my screen?
Yes, sir. Your screen is visible.
All right. Just let me just this thing. What I'm going to talk to you is a failure investigation. Actually, it pretty much aligns with your workshop title. It's about grid resiliency, but we'll see how far we go. But what it is, it's a MICA is a big generating station in British Columbia Hydro. British Columbia Hydro is in Canada. It's in the western part of North American hemisphere, right northwestern. If you know California, go up quite a bit north of California. California followed by Portland, followed by Washington State, then starts Canada. That's where the British Columbia is. It's a northwest part of North American continent. So British Columbia Hydro is a large hydroelectric utility with 10 gigawatt of generation. So what I'm going to talk, one of our incident happened in one of our large generating stations. I think I'm just going to, for lack of time, I'm just going to skip some of the slides fast. In any investigation, you have team of people. These are my colleagues or my friends who have my staff, my colleagues, whom I call some of the experts who contributed to this forensic investigation of a failure. And I'm just going to skip some here. I think there are some symbols in my presentation. I will explain all the symbols as I go along. And I'll provide a copy of this presentation as well as a paper, IEEE paper written on it. I'll provide both of them after my presentation to your organizers, and you will have the copy of presentation. So don't get too disheartened if if I'm going too fast. I'm skipping the slides which are much more background information, but I'll go through all the key slides. What you see here is a very simple diagram. This is a hydroelectric generation. How electricity basically in a typical utility system get transmitted from a large centralized generation facility to an end customer. Although the grid architecture is changing, it's migrating from centralized architecture to distributed architecture. So I think grid resiliency and all people talk in the context of distributed architecture. I'm talking in the context of centralized architecture, centralized generation. So if there's a large centralized generation, we step up the generation to a transformer into extra high voltage system or very high voltage system. So in British Columbia Hydro, 500 kV system. Then you can step down to a lower voltage sub-transmission system, in our case 230 to 66 kV, and then you go to the lower voltage 25 kV distribution system. But I'm going to focus on this extra high voltage system. This extra high voltage system, in our case, is a 500 kV, in India 400 kV and 700 kV system you have. What happens if this transmission, basically what this extra high voltage system allows you to transmit electricity from a centralized generation, which happens to be a large generation facility. Centralized generations are large generation facilities, like in this case happens to be hydroelectric. And when you're transmitting this power over a long distance, you use extra high voltage or high voltage lines. If you use extra high voltage or high voltage lines, they are long lines, long transmission path, 200, 300, sometimes even almost 400 kilometer long lines. And then those lines, what we call, have a Ferranti effect. Basically, if the line has an inherent capacitance, that capacitance, if you leave the line disconnected here or lightly loaded, the voltage at the receiving end can be much higher than the sending end. So in order to make sure the sending end voltage and receiving end voltage are close to rated voltage or 1 per unit voltage during light load conditions, we put the shunt reactors. These are the shunt reactors. Basically, what shunt reactor does is counteracting. It's a bulk reactor which is counteracting against the capacitive current inherently drawn by the line. That's what it's doing. So that's just to tell you this is just to tell you why we need a shunt reactor. Now we have a shunt reactor. So just before I go, I'm going to tell you a little bit more about the system. So we have a large generation facility which is about 3,000 megawatt. It is getting, and there's a transmission path, existing transmission path from here to here. The line has a shunt reactor here, and it connects to the integrated grid here. And let's say the path reactance is axle, the transmission path. It's going through a long 500 kV line, which is 277 kilometer long. So this is our centralized generation. This is our grid. So the electricity is transferred from here to here over a transmission path, which is in this case happens to be almost 300 kilometers. And we maintain the voltage at both ends to about rated voltage by putting shunt reactors. One shunt reactor here, one shunt reactor here. So how much steady state power transfer limit is? Steady state power transfer limit is given by, as you may know, given by V1, this voltage, multiplied by this voltage, divided by path reactance, XL, and sine of delta between them. So the maximum, if we have a 1 per unit voltage here, 1 per unit voltage here, so the steady state limit will be sine delta over XL. Basically, the megawatt transfer is limited by the line length or inversely proportional to the line reactance. Basically, the path transfer limit is inversely proportional to the path reactance. Now to double, let's take it, we want to increase the capacity, the path transfer capacity, we want to increase the steady state limit. We could add, what we need to add another path. If you want to double the path transfer capability, if you want to make this to twice as much as this, we need to put another path which is in parallel. Now that's expensive. It takes not only billions of dollars, there is always a resistance from members of public that they don't want no one wants a transmission line in their backyard, and a lot of environment footprint. There's quite a challenge to build a new transmission line. So there are alternatives. What is the alternative to building a transmission line? Is add a series compensation in the transmission path. So let's take it, you add a series capacitor in between the transmission path, such that series capacitor is this basically XL minus. So basically the path reactance is reduced. As a result, your transfer capability is increased. So easy way, quite simple way to increase the transmission capability of a path or steady state transfer limit of a path by adding a series capacitor in the middle of a line. And typically we can add easily up to 50% of the compensation. Going beyond 50% compensation introduces some other technical problems. It can be done. It introduces some voltage inversion, current inversion problems. They can be overcome with with extra care. But 50% compensation is it's much more simpler than more than 50% compensation. Basically, by putting a 50% compensation, you can double the path capacity. That is mean you can avoid building a full transmission line. So basically, now the path transfer limit is 1 over XL minus XC, sine delta over XL minus XC. So to double the transfer limit, X is equal to minus 0.5 XL. Now, nothing is free. There's no what we call as a no free lunch in the world. You don't get a free lunch. You get a cheap path increment. You get a high increase in path capacity just by adding the series compensation, which costs maybe 40, 50, $60 million, maybe $100 million, maybe. And building a line is in excess of 300 kilometer long. Building a 300 kilometer line will cost you $2 billion actually. So quite a economic solution, fraction of a cost. But nothing comes for free. There are problems with series capacitor. The line has inductance. That's not what line has to start with. It's a 50% compensation here. So line has a reactance, which we call it as XL. Plus there is a reactance here too. All that they form a series path. So you see XL, in this case, I just took a simply, right now I'm taking a very simply the line reactance and the shunt reactor capacitance. Shunt reactance is 50% of the line reactance. So basically, the natural frequency of a series circuit, the natural frequency of this series circuit, there's a source here, there's a system, the load here. If we ignore the shunt reactors here, we can ignore them. Just take this series path, take this path. The resonance frequency of it is less than 60 Hz. For a 50% compensation, if the source impedance is 0, it's a 30 Hz. If there's a source has the impedance, and the other terminal has some impedance, it will be more than 30 Hz. So what I'm trying to make a point, it forms what we call sub-synchronous resonant circuit, less than 60 Hz resonant circuit. And if for any reason, for whatever reasons, this sub-synchronous resonance gets excited, then it can form what we call sub-synchronous oscillator. And there's a very little damping in a system, and that can be a problem. If there's a light load or there's no load on a system, it can damage the equipment. Now, before I go to that incident, I do also introduce a topic called point on wave controller or point on wave switching or point on wave control switching. So let's take it, you have a source here and you want to energize a transformer. When you energize a transformer, if you energize a transformer at voltage 0 here, what you're going to get, you're going to get a lot of inrush current. Basically, we get a voltage 0. You get at voltage 0, your flux should be 90 degrees. The transformer is demagnetized. Half a cycle later, your flux will double, basically. So I think I'm just skipping fast. I assume all of you know, if you energize a transformer at 0 voltage, transformer will experience a flux doubling effect, and that will cause a high inrush current due to transformer saturation. And if transformer has a residual flux, then you can build a flux as high as close to 3 per unit. That will cause a severe saturation, and inrush current will be very high. So how do we avoid? I think this is the explanation of the inrush current. Like I'm just going to skip. But I wanted to introduce a topic. So how do we avoid this large inrush current? Old days, when we had air blast circuit breaker, if this circuit breaker was air blast, we had a pre-insertion closing resistor. So before closing the main contact, we would close the auxiliary power. We will close the auxiliary contact. We can add a resistor to the circuit, and then we close the main contact. As a result, we have. So basically, we add this resistor for a short duration, 400, for example, 400 ohms resistor for a 18 to 16 milliseconds for one cycle kind of thing. And after the main contact is closed, after 16 milliseconds, we take it out. That's the way we manage. How we manage. Is everyone with me?
No, I can't teach too much. I just want to teach without me.
Can you please mute who is talking? Right? So the modern breakers. Thank you, Himanshu. The modern breakers are SF6 breakers, and they come up with a so-called, I don't agree with this new more modern technology, and this is what I'm going to talk about. This modern technology is called point on wave switching. What it does, it tries to switch a demagnetized transformer, assuming your transformer is demagnetized. It tries to, instead of it switches on a voltage peak so that your inrush, your prospective flux is equal to the residual flux in a transformer. So if it's a demagnetized transformer, you switch at a peak, your flux is zero, your voltage is maximum, you have a smooth transformer energization, and you experience no inrush current. So controlled closing of a breaker at a peak of voltage waveform performs smooth transition of a transformer from de-energized to energized state without exciting any resonance or anything. So what happened in this incident? This is a detailed circuit diagram of a system I'm trying to show. This is a large generating station connected by two transmission lines. There's a grid. When this event happened, one of the lines was out of service, and we were trying to so I'm just going to show a simplified diagram of the system. This is a simplified diagram of the system. So what we were doing, we had a transmission line. We were just picking up this transmission line from here. So this system was de-energized. Our objective was to pick up we were trying to pick up this 4 transformer, 1, 2, 3, 4 transformer with this. So red mean closed. So this breaker is closed. We were going to pick up 4 transformers with this breaker. We are going to pick up this line from one of this breaker, and so and then this series capacitor is in the circuit. So line is gray mean line is energized, de-energized right now. Gray color mean everything is de-energized. Dark color mean everything is energized. Green mean breaker is open. Green mean breaker is open, and so we're just going to go through the sequence here. So this breaker was closed, line got energized. Look, everything became black. So everything became black when it got energized. So series capacitor got energized. This breaker is open. The series capacitor. This breaker open means series capacitor is in the circuit. We closing this breaker. So go back one step. All this is de-energized. Gray area is de-energized. I'm going to close this breaker. I'm going to energize everything. This breaker is open. Look at this. All this path got energized. This transmission line is energized. These 2 shunt reactors are energized. These shunt reactors are energized. Everything is energized. Now, I want to close this transformer using a point on wave control, smooth closing. Once I close this transformer, I expect all this thing to get energized. Only the generators are offline, these breakers are open. So my objective is to energize this 4 transformer using this point on wave controller. POW means breaker equipped with point on wave controller. I do that. Yes, everything went very well. Everything got de-energized. Transformers is drawing a magnetizing current. Boom. Oh, something went wrong. 200 milliseconds after the transformer was energized, this breaker opened, tripped. How? What happened? Then, story doesn't stop here. Then, 300 milliseconds, this transformer faulted, had a major arcing fault. And then this reactor, this reactor had a major fault. Its protection operated, sent a signal. Once this protection operated, it only gets clear. There's no circuit breaker. We don't open the circuit breaker of a reactor for reasons not covered in this presentation. So this protection operated, basically de-energized line, open these 2 breakers, and it was already de-energized there. So we de-energized everything after 300 milliseconds, but we had fault in this reactor. Look at later on, the reactor, look at this, a twisted tank cover. I'll show more pictures later on. Forensic analysis, what happened? So go back to my original diagram. So what was the circuit? We had a switch yard, which is a source. Source was the switch yard. This was the source. This is my source. This is my switch yard, is a source there, not the generating station. I'm picking up a line. I'm just watching my time too. Please give me a signal when you want. 10 minutes before conclusion, I give 10 minutes per question. So I close up. So This is the source here. This is the source here. I energize the line. So this is the circuit. My source, I close this line. Capacitor is energized. Reactor is energized. There's a reactor here. I'm not showing for the timing, just for simplicity. Thank you. So then, this is a reactor is energized. This is a transformer. This is shown as a transformer magnetizing impedance, just shown here. And I'm going to close this transformer in a point on wave control. My intent is to close this transformer on a peak for a smooth transition. And unfortunately, it got energized not at a peak. Something went wrong in a controller, and it got energized at a non-optimal instant. And this, when it got energized, the flux got 2 to 3 times got built up in this transformer magnetizing impedance, and it excited the circuit here. So it's excited what we call ferroresonant sub-synchronous oscillation. That's what it did. This is a resonant circuit got formed with a now reactor is right now not playing a big part. The line reactance and this in series with this, and this is saturated iron core. And since transformer was energized unloaded, there was underdamping to subside oscillation. In fact, we had a negative damping, and I'm going to ask, maybe just in a minute, I'm going to ask a question from audience. So look at the waveforms. This is before energization. Source voltage was quite nice, 60 hertz. We energize at this point and look at the chaotic. And look at this. It did not, the voltage and the point on wave controller did not close at voltage peak, instead closed much later. And it was a non-peak switching, and we started a chaotic. This is the voltage. Just look at the voltage before and after. That's not very good. It's a chaotic voltage after switching. And I'm going to go, and we did a spectrum analysis of this waveform. The spectrum analysis of this waveform is already there's a 60 hertz voltage here. This is 60 hertz synchronous frequency, source frequency, or damping or forcing function. 60 hertz is the forcing function. 20 hertz is the resonance frequency, sub-synchronous resonance frequency, 30 hertz. And look at the currents that's going in the line. And these are the same voltages. In the last slide, I showed a single phase voltage. These are the 3 phase voltages. All 3 voltages are so chaotic, and these are the currents. That current is flowing in the line. And look at the current, the transformer inrush current. Instead of inrush current has a very first peak very high, then it reduces. Look at here. It is not reduces, it is a negatively damped. I'm going to mute. I'm going to ask a question. I'm going to ask a question from audience. Why do you think what could be one of the big reasons for the negative damping? Can someone, if someone knows, please unmute yourself and answer, otherwise I'll provide the answer much later. Can anyone guess that? If not, I'll come back to that answer later. So look at this, we have a negatively damped oscillation. At this point, I just said the protection operated 200 milliseconds later after energization, protection operated. There was one other transformer electromechanical protection operated at this point and disconnected the transformer. And 100 milliseconds later, we had looks like A to C fault in a reactor. A to C fault, look, equal and opposite current. A to C fault in a reactor which started small and then became very big. And at this point, finally the reactor protection got tripped and isolated the reactor, and event came under control. I think I'm going to leave this part out. At this point, we lost the signal from a CVT or the voltage transformer because the overloading caused by sub-synchronous resonance. Now look at this. I divided this into 4 parts. Line currents before energization was simply reactor current. The reactor is drawing some current, which is then these are the 20 hertz ferroresonance current before the transformer trip. This is the time when transformer got energized for first 200 milliseconds. At this point, transformer got de-energized by the protection because one of the transformer protection operated, was not supposed to operate. Transformer protection was not supposed to operate. We were thankful it operated. It disconnected. I'll explain later why transformer protection operated. And then there was a 100 millisecond of 1300 ampere of current flowing of 9 Hz frequency. The reactor. This reactor was drawing after this transformer trip. This reactor started to draw 1300 ampere of a peak current. This is 1300 ampere peak current, and the frequency of this current was 9 Hz. Before, at this point, it became a full 60 Hz fault. This is here it became this reactor had an A to C, looks like A to C fault, and this is a pure 60 Hz short circuit current waveform. I want to draw your attention to this circuit. This is a capacitor, is a 56.6 microfarad, 50% compensation. If you take the impedance, convert it into farad, that's what it works out to be. Add the line, I ignored the line capacitance just for simplicity, and took the impedance of this reactor impedance, and this reactor impedance is for 5.4 Henry, and you calculate the resonant frequency at 8.9 Hz, which exactly matches with it. So this is also this reactor, the reactor steady state current. This was a steady state current of a reactor, which is about 140 ampere. Steady state current of a reactor is 140 ampere. Now, because it formed a resonant circuit, so instead of 140 ampere, it is drawing 1300 ampere. See, this is the current when before energization of a transformer. That is, mean this was a reactor current before the transformer was energized. After transformer was energized, this is the total line current, and transformer got tripped. At this point, this current should be equal to this current. No, it is not. It is not equal because the resonant circuit is formed, and we are having a 1300 ampere of the current. So basically, I divided my circuit into 4 parts. Sorry, I divided my event into 4 parts. P fault, ferroresonant part, resonant part. The reason I call a resonant part, ferroresonant means this transformer magnetizing impedance was playing a very important part during this part. Therefore, we had a frequency of 20 Hz. These two together and this nonlinear impedance form 20 Hz resonant circuit with this capacitor. That's until this point. Once this tripped, this is an air core reactor. It does not saturate, so it forms a linear resonant circuit. So therefore, we have 4 parts: pre-fault, ferroresonant section, resonant section, faulted section. And if you look the contour analysis, this is nothing but spectrum analysis of current in contour format. So before the fault happened, yellow color means 60 Hz, blue color means DC, or like a 0 frequency. So in this contour, look at 60, the spectrum is 60 Hz, is a very predominant frequency before the event, before we switch the transformer. After we switch the transformer, we have a predominant frequency is about yellow color is mostly at 20 Hz. At about 200 milliseconds after switching, the predominant frequency is switched to the 9 Hz linear part. After 300 milliseconds, when A to C fault developed, frequency went back to 60 Hz. So this is the full event. Now I want to make one more point. Look at this thing. Look at this thing. There are no zero crossing. There's a lot of DC offset here too. And I call it this was a blessing. Sorry, not a blessing, I apologize. There's a DC offset. At this point, for any reason we had opened this breaker. If this breaker was opened during this time, this new modern breaker, SF6 breakers, cannot handle any amount of DC offset. They cannot handle 100 amperes of DC offset. This is a 1300 ampere current, which has about 1000 ampere of a DC offset. So this amount of DC offset, these breakers cannot handle. So if we had caused any trip in this point of this breaker, we would have a breaker failure. We would have exploded this breaker. This breaker would have exploded catastrophically, could have hurt some people sitting in the station. But what happened, that the fault happened here, which masked the fault current was about quite very high, which masks this DC offset, and allowed this breaker to open successfully. Actually, we have a multiple, every year we are losing 2 breakers because of this problem, because of point on wave technology. That's another topic of discussion. I'm not discussing today. So we would have caused this breaker to fail in a bad way. And this is a failure. Actually, we had a similar failure in our company in 2012, 2016, 2018, 2020, and 2022. We are almost on average every year we are experiencing a breaker failure. That is because we are applying point on wave controllers on a long, highly shunt compensated line. That's a topic for different discussion. Now, what I wanted to get back to you, we thought we had a A to C fault. But look at this reactor. This reactor is this is a single phase 3 reactor. 500 kV reactors are in single phase format. One reactor A, B reactor, C reactor. They're physically apart, 32 feet apart. It was not making a sense to us. How come it's a A to C fault without involving B? How a fault R can go from here to here without touching B? That was not making. The electrical signals were telling us that A to C fault, but physical construction was telling it's not A to C fault. We needed to do more investigation. Yes, more investigation did lead a result. These reactors have a neutral reactor. Look, there's a neutral reactor for single phase stripping and reclosing on this line. Again, so this could not, anyway, again, I'm saying we could not have A to C fault. So what happened? Actually, what happened when we really, we didn't have the physical evidence. So we thought about it. We thought, no, what has happened? Our analysis or our gut feeling was telling what has happened. The phase A has faulted to the neutral, phase C has faulted to the neutral, and because of this high impedance, it is appearing like A to C fault. Actually, it is A to N fault, it's a C to N fault. And being a high impedance grounded, it is looking like A to C fault, but we did not have a physical evidence to confirm because of all this. There was a cooling oil. These are air core reactors, but there was oil. The reactor had to be detanked and then dried, and then someone had to go and do the investigation. Yes, we did the investigation, and I'll show I had a picture. I'll see if I can show later. We did investigation and found, yes, it was A to N fault and C to N fault. But the resiliency part, I wanted to make a point. It is a large facility. Our management got quite worried. They were not allowing to bring this generating station back into the system because of this failure. They were worried, what if this breaker explode and the people get hurt? So I was in the middle of it, and really I came up with a plan, very careful plan from a grid resiliency point of view, because we could not leave this plant out because that would have been our reliability risk. So I needed to restore the plant back. So I came up with a plan, exactly opposite plan of how we started. I said, okay, what we are going to do, we are going to spin this generator, close this, we'll spin this generator with this breakers closed so that this transformer has a soft start. Basically, we start with a zero flux on zero excitation on this. Transformers that are not energized. When the flux builds up in a generator, voltage goes up, the transformer has a smooth start. So there's smooth start, no energy, no fluxes, like, no inrush current happen. We will close this breaker with de-energized system here, and then we'll pick up this line, and then we will close the line here with a synchronizer, not with a point on wave. We'll close the line with a synchronizer. If anything goes wrong at this point, even if anything goes wrong at this point, we have a system load which will provide a lot of damping. Even if we set up, and sorry, one more thing. I suggested we are going to bypass this series capacitor. So the precautions I took, we are going to do a soft start of the soft energization of transformer, back energization of transformer by starting the generator and the transformer. This breakers closed, transformer connected. This is a smooth energization of a transformer. We'll close this breaker. This series capacitor is bypassed. We'll pick up the line, and when the full line is energized, we will do under synchronizing control and not under point and wave control. And then we will have it no damping. So we had multiple things, multiple checks and balance taken. The risk of sub-synchronous resonance was avoided by bypassing the series capacitor. A lot of damping was provided by system load. So there was no risk, and we restored the plant quite fast within days. And I think that's one of the things people, I feel very proud. After such a major incident, we had this 3,000 megawatt generating station back online within days. Basically explaining black start, series capacitor bypass, synchronizing switching. These are the steps we took, and this is how we energized the system, brought it back within 4 days. Okay. We did all analysis. I'm not going to go through analytic. We did EMTP modeling. We were successful in modeling. This is our showing our model versus recorded waveform. They're pretty much similar. We were able to model. Once we model, we came up with a recommendation how to overcome the problem for future. The thing which I suggested to come up is we have two breakers. We have two breakers here, one breaker here and other breaker. We have actually go back. We have two breakers here, one breaker here and second breaker here. And these two breakers, one of the breaker is a double chamber breaker. This has a double chamber breaker. This is a single chamber breaker. The single chamber breaker is like that. When it opens, it's open. But double chamber breaker have a one good property. What good property they have? They use what they call the capacitor, grading capacitor across two contacts. Double chamber breaker against each chamber, the grading capacitor. And so there's a source here. The source keeps the voltage current going, low amount of current going this way, and keeps small amount of current flowing into the transformer. What is the benefit of this is grading capacitor. I'm just going to skip this slide and going to see that benefit of, sorry. Okay, I did not have that slide, but I wanted to explain what that does. I had another slide which I cut it down for this presentation because of time. What this grading capacitor does, that it keeps it energized. Basically, what it does, it collapses. It collapses the hysteresis loop of a transformer. Once it collapses the hysteresis loop of a transformer, the transformer is de-energized. We don't need to know what is the residual flux in a transformer. All we need to do, point on wave, the optimal instant is always peak voltage. But if we energize the transformer through this thing, we need to estimate what is the residual flux in a transformer and change the switching angle. So one of the things which I recommended is to maintain our point on wave controller properly, that it has no drift, because a point on wave controller drifts. This is the optimal instant. If the breaker time drifts by 4 milliseconds, you will have from best case to the worst case. We don't want to do that. So recommendation was, we will energize the transformer with this breaker, which will collapse the hysteresis loop, means there is no residual flux, and we will maintain our breaker so that there is no drift in it, and we will always switch at this instant. And I think at this point, I'm just going to leave it, my presentation. And because the time is up, I did ask a question about why there was a negative damping. The answer is, when you have an induction machine or synchronous machine, when you slip at sub-synchronous frequency, your slip is negative. So your impedance is R over S slip. R over S is negative. Your resistance of the system becomes virtually negative resistance. That's called a negative damping. I think my time is up. If there is a quick question, I'll be happy to answer. Otherwise, Diksha, back to you.
Thank you so much, sir. So we have a question here from Mr. G.
Diksha, you're mute.
Hello. Hello, am I audible?
Are you able to hear me? I can't hear you, Diksha.
Hello. Hello, am I?
Hello, Diksha.
You are audible, Diksha.
Diksha, you are audible.
I lost the sound here.
Okay. Perhaps sir can hear me.
I was able to hear you earlier. Have I put myself on a mute or something? I can stop sharing and see if you can hear. I can hear you.
Can you hear me now, sir?
You are mute, Diksha, for some reason. Ask to unmute. It's telling ask to unmute. It's showing me your screen is mute. Somebody else has to
Can you
unmute.
hear me now?
Okay, I'm unable to hear. Sorry, it's still showing your screen is mute.
Hello.
I'm mute too now.
Now?
Oh, there are some. Can you hear me?
Sir, you're audible. You're audible. Can you hear any of us? Atul sir, can you try once?
Yes, Diksha, actually, both of you are audible.
Yeah, but are you audible to
I
Mukesh?
can't hear, so I will just read the question and try to answer it.
Yeah.
Is it time for me to answer the question?
Yes, sir.
I can't hear you, Diksha, unfortunately.
Yes.
Okay, can I answer the question? Okay.
Yes.
Okay. Will sub-synchronous resonance generated due to capacitive compensation effect of electromechanical oscillation? No, the sub-synchronous was not. In this case, no. In this case, sub-synchronous resonance was generated due to the capacitor of the series capacitor and the reactance of the system. The generation was that the switchyard. The generation was quite far away from the source side. Like we energized a line from a switchyard, and the source from the switchyard was far away. No, and we have a hydroelectric unit. We do not get excited sub-synchronous. We do not have a sub-synchronous resonance point. So no, it was not from the mechanical oscillation of generator. Mechanical oscillations are generally typically in thermal generators. We have a hydroelectric. Sometime after clearing the source. So that was the question from Jitendra. So next question is from Subhamba. Sometimes after clearing the fault, network becomes the radial. The radial overcompensation causes sub-synchronous resonance, especially in wind farm. So what can be done to avoid? Very good question. We have seen in Texas that problem. So the protection for them, what you need is a sub-synchronous resonance relay, which can detect sub-synchronous resonance frequency, like it can operate. Given once the relay detects the system is oscillating at sub-synchronous frequency, you can do two things. A, trip the line. That will not help because the radial system, you lose the system. Send a signal to bypass the series capacitor. That's one of the easiest protection against sub-synchronous resonance in the case you have asked. I think there are two questions only. Now everyone is saying they are hearing problem. I'm not able to hear anyone, but as long as you can hear, that's good. A general question, may I know what are the protection textbooks we have followed so far? Oh boy. Actually, I do not. Regretfully, I teach two courses. I have my own notes. I have not written a textbook. I don't follow any textbook. The reason I don't follow textbook, I'm a practicing engineer, and I teach protection very much what practices which I've learned, and I don't enjoy teaching a textbook course. I've designed my own course, two courses, and I try to teach a very, very hands-on practical course. So I don't follow textbooks. So there are many good textbooks, but I don't use them. And then is there any more question? I'm not audible. We had a rich. Okay, all right, thank you. All right, that's where I think I've covered all the questions. I apologize, I'm still not able to hear you, but that's okay. As long as you can hear me, that's good. And I don't know if I have any control to do that. If I have anything control to unmute.
And now we are not able to hear you.
I'm sorry. Yeah. You are muted. I am muted. Okay. All right. So is there any more question, or my time is, what is the importance of communication in modern distribution network protection? Okay. Can I take this last question, Diksha?
Yes.
Okay. What is the importance? When you start to connect distributed energy resources, it all depends how distributed energy resources connected to your network. One of the problems happens when you connect a small resource to a network. If that resource become islanded with a line, that source has the source has a what we call the source has a very high source impedance because it's a distributed resource, it's a small resource, its impedance is very high, and the line has a natural shunt capacitance. Again, when it becomes islanded with the source, it forms another series circuit and forms a near 60 Hz resonance. So in that case, with a weak source, long line, you see a Faraday effect, the voltage goes way higher. The resonant voltage goes much higher than 1 per unit. And that's where the communication type of a protection we use. In those scenarios, we do use communication protection. Actually, I have a paper on it. I will share. I can send it to the organizer on this specific topic. So what we do, if we see a islanding condition, we send a direct transfer trip to disconnect the distributed resource. So what are the applications? Another application is a multi-terminal line protection. That's another application in the distributed resources. So communications are playing in protection a big part, as well as in control and management of distributed resources. Any more questions? So if I'll just see if there's anything in the chat line still. Okay. That's all. I don't see any more new question. If Diksha, again, I'm sorry, I'm not able to hear you, but thank you for putting up with me. And my apology for being late once again, and wish you all of you very happy day. Thank you very much. Thank you. I heard you. Thank you. Wish you all very happy day and enjoy your rest of the day and your lunch and everything. And for me, time to go to sleep very soon. I'll have my last cup of coffee, my coffee, and then I'll go to sleep after that. And wish you very happy Diwali. Yes, happy Diwali to everyone. It's on Monday. Is it on Monday or I always get confused? Yeah, one day we get fixed. So what time? When is Diwali in India? Monday or Tuesday? Monday. Thank you. So I take day off on Monday. Thank you, Diksha, and thank you for hosting. Wish you very good day.
Hello, am I audible to anyone?
Yes, Diksha, you're audible.
So we'll start the next session in a few minutes. We have our next session by Professor Bharat Singh Rajpurohit, and the title of his expert talk is Electric Grid Integration of Renewable Energy Sources, Key Issues and Challenges. Hello, sir. I, Diksha, on the behalf
Hello.
of IEEE SBC IIT Kanpur, welcome you to PERA 2020-22.
Okay, so thank you, Diksha, and I'm thankful to IEEE student branch at IIT Kanpur and UP section also for giving me this opportunity. I did PhD from IIT Kanpur in 2009 with Professor Singh, and it is always a great pleasure to be having interaction with IIT Kanpur fraternity. So thank you very much for this. So I'm having around 1 hour. Is this fine?
Yes, sir.
And the participants are mostly the research scholars of IIT Kanpur.
Yes, sir. We also have some participants from outside IIT Kanpur.
Okay, okay, fine. So then it would be mostly students, it seems to me.
Yes, sir.
Yeah. Okay, then fine. So
I'll just introduce you to the audience once, and then we can start the talk.
then it is fine. Okay, please go ahead.
Yes, sir. So Professor Bharat Singh Rajpurohit received the MTech in 2005 from the Indian Institute of Technology, Roorkee, India, and PhD in 2009 from Indian Institute of Technology, Kanpur, India. Presently, he is working as professor in the School of Computing and Electrical Engineering at the Indian Institute of Technology, Mandi, Himachal Pradesh, India. His research interests include power electronics and grid integration of renewable energies. He's a senior member of the ISTE and the IEEE. The title of his talk for today's event is Grid Integration of Renewable Energy Sources, Key Issues and Challenges. With this, I would like to hand it over to Professor Bharat Singh. Sir, I would like to have your permission for recording this session.
Yes, fine.
Sure, sir. Okay, sir, you may start now.
Yeah, and let me share my screen, and for a proper bandwidth, is this fine? Should I stop my video? Is this fine?
I think it's good, sir. You can do both.
Fine. Let me then first stop this and let me share the screen, and please see if you can. Is this slides are visible?
Yes, sir, it's visible. You can just go to the full screen mode.
Is this in a full screen now? Is this in full screen now?
Yeah, now it's in full screen, sir.
Okay.
Yeah.
So fine, then I can start. Will take
sir,
around 50 minutes, so that we will be in time and can have some discussion. And I request all the attendees also, please feel free to let me know whenever you would like to have some discussion on any part. So once again, thank you. And today we'll be discussing about that when we are doing a large scale grid integration of renewable energy sources. So then what could be the issue and challenges? There are two major issues could be there. One is about the technical and another one is the regulatory one, policy based or financial based also. So we can based on the time we can discuss both of these issues in a certain manner. Before moving further, let me just briefly tell that IIT Mandi is situated in Himachal Pradesh. It is around 450 kilometers from Delhi, 200 kilometers from Chandigarh, and is very close to Manali. So from our campus, we are able to see the snow-capped mountains are there, and we are almost of 2,000 students, 150 faculty member, and institute is already got established fully. Broadly, this is a bit old photo. The campus is divided into two major parts, North Campus and South Campus. Now it is connected through a road, and it's a hilly terrain you can see. Then we have a couple of different schools at IIT Mandi and a few centers also. Center mostly housed the advanced instrumentational facilities for teaching and research. And we are having a very strong group in the area of materials. So that is our stronghold. And also we have established a clean room of class 100. In that also area also we are very strong here. So IIT Mandi focus other than the green energy technologies is materials, integrated mountain development, and agriculture and food processing technologies also. The School of Computing and Electrical Engineering broadly offers BTech degree in electrical engineering, computer science and engineering, data science. We are also offering MTech in powertronics and drives, VLSI, communication and signal processing. And recently we have started MTech in electrical transportation and a MTech in computer science. Then we are also offering 3 years of MS by research and PhD program also. These are the couple of pictures, not very recent, but couple of pictures you can see of IIT Mandi campus. It is a North campus. In between, you can see a couple of hostels and a few academic buildings are also there. So you can see it is giving a look of a very big village of a mountain area. So now coming with the current topic of discussion, that we are aware of that in a current scenario, we want a address couple of issues, especially related to the energy in the terms of electrical power. So security of supply is important, and sustainability is also very important, and there are many solutions out there. To achieve these problems, the major solution which most of the countries and India is also looking forward is to have a larger penetration of renewable energy in our system. Then when we talk about renewable energy sources, then two major players are there, which is wind and solar power, which will be able to get installed in very fast manner, and once they are having a large installation, they will be able to replace the conventional power sources also. So that is very much possible. Just for an example, a single wind turbine can be of a more than 10 megawatt single unit, and similarly big solar farms can also be there, ranging a couple of hundreds of megawatts. So that is very much possible. Obviously, when we are talking about such sources, then there are few challenges are also we are able to see. A very natural challenge that we are able to see is about intermittency, which is based on the source of the energy, which is solar, irradiation, and the flow of the wind. So these two are also very important aspects. There are few minor issues are also there. Slowly we can see also them. The government of India has invested heavily since 1981 by giving a complete ministry known as Ministry of New and Renewable Energy, which promotes the renewable energy by different way. The renewable energy integration or utilization can be broadly divided into two categories. One is the grid integration, another one is distributed one or a off-grid manner. So we will be more concerned about the large-scale grid integration manner, and as you are aware of that the society of communities and the society of our country are already having very good practices of utilizing the solar energy in many sense as compared to the North America or the Europe. So that is already got inbuilt in our day-to-day practices, and slowly we are also increasing by having many innovations for large-scale grid integration, as well as of many devices which will be able to provide the off-grid utilization of the renewable energy sources. Government of India have provided many incentives, subsidy to promote renewable energy sources. Some of them are only for small interval of time, generally known as like generation-based incentive (GBI), which were there to promote wind penetration, but not only the wind penetration level with a grid connection, but also to generate more and more energy. So that's why there was known as generation-based incentive. They have also provided many income tax benefits also, and tax benefits also. So this is what there. And slowly with the Electricity Act 2003, many regulatory framework were also introduced so that the such renewable energy sources can be promoted. And nowadays, generally, these are treated as a must-run system. So it promotes the renewable energy sources. Fine. Current situation is also good. We are having around 400 gigawatt installed capacity. Out of this, around 100 gigawatt is from the renewable. And recently, in last couple of years, solar has increased its penetration level very high. Earlier, the wind was a bit at a higher pace in terms of renewable energy integration, and India is also standing somewhere at fourth rank in the terms of installation on the wind. We are having good centers also known as national institutes to promote different technologies and to specially do a certification also, which includes Center for Wind Energy Technology in Chennai, Solar Energy Center in Gurgaon, Alternate Hydro Energy Center in Roorkee, and similarly for other sources also. But when we are talking about that which is the key driver which promotes the renewable energy into the grid, so other than the requirement of the clean sustainable energy source, a regulatory framework is also being introduced which is known as renewable purchase obligation. I'm sure some of you have already heard about this word, but what is this RPO? RPO stands for a obligation to purchase renewable energy, which is a minimum amount of renewable energy source energy for in a given time frame, that in a given financial year, by the respective utilities in the states to meet the mandatory electricity energy requirement. So this is obligated and by the utilities of a state, and the targets are given by the state electricity regulatory commissions, and this RPO requirements are divided into two categories. One is known as solar and other for the non-solar. Due to the earlier the price difference between the solar and non-solar was very high. This is why it's given in the two different targets for the renewable energy. And if it is not being met by the utilities, then there is a penalty clause is there. So nowadays this is strictly being followed and being mandated. So this gives a obligation with some penalties to the utilities to purchase or to utilize the renewable energy in a certain sense. But how these targets are being given? The targets are given by the overall national action plan on the climate change, which gives that how much percentage of energy should be by the renewable energy. And based on that, different states are there. These targets are being distributed among them, and each state electricity regulatory commission, based on how much possibility is there and opportunities are there, they are deciding on this target. So this is how these targets are being you can say given, and it is being met. And slowly we are also able to see some of the states which are not having the renewable energy sources, which depends on nature also in a particular state, then the states may raise the issue that how they will be able to meet this RPO requirements. To achieve that, another regulatory framework known as renewable energy certificates are also being introduced in the country, so that if a state is not having a renewable energy actually in the state, they are not able to get based on bilateral contract, but they will be able to procure or buy those certificates to make sure that they are able to meet the RPO requirement. If the time permits, we'll discuss very briefly on the terms of renewable energy certificates also. Till now, if you are having any query or any comments, you please let me know, or you may also write in a chat box also. We'll see periodically that chat box, and if some query is there, we will be able to discuss it furthermore, right? So as we have discussed, with high penetration of renewable energy sources, we need to make sure that the system remains in a stable manner, system remains in an intact manner, and could be able to serve the loads. But with the increased penetration of wind and solar, which is mostly based on the small asynchronous generation or converter interface energy sources, another challenges are there, which is to meet the grid connection requirement, or known as grid codes also. Different countries have issued the different codes. India is also have a grid code for the renewable energy generation is also given. So it means as the penetration level of wind and solar or renewable energy is high, the earlier adopted practices are not now tolerable. What were the earlier practices? Earlier practice was that during a abnormal condition, the wind or solar farm can be disconnected from the grid for their safeguard, for their safety, or especially for the powertronics converters. But with the penetration level is high, we have already backed down a conventional generation. So such type of loss of connection is not allowed. So this is what a important concern in the terms of grid codes, or to maintain the stability of the system. Then another issue was that intermittency was also there, that whether a committed generation can be, which is scheduled, can be met by the renewable energy source or not. Then how to integrate that particular intermittency issue in our scheduling and dispatch process. So that becomes also a challenge for a regulatory bodies. And obviously another one was that high cost of a power generation. But when we talk about external and internal cost of another sources, whether it is a thermal power station or renewable energy sources also, then many researchers have challenged that we should incorporate those external or internal cost also. External cost generally means that if a thermal source is there, then what will happen to the fly ash, or to address the issues of the climate or the pollution due to the thermal sources, how to address those. So those costs, if we are going to include, then obviously they will be high as compared to the renewable energy sources. So such type of costs are also being factored out by many researchers. So in broadly, we are having two issues. One is the grid connection issues when a large penetration is there, or another one is a economic issue due considering the high cost of the renewable energy sources. So broadly, this can be intermixed and can be talked as a system operational aspects. Is there any query or question till now? Please let me know. Should we move forward?
Yes, sir.
Okay, fine. So when we are talking about the grid connection issue, then what are these grid codes are there? So these grid codes can be considered as a minimum technical requirements or guidelines for connection of the renewable energy sources with the grid. And this is broadly known as grid codes. India has an Indian electricity grid code is there, in which with other requirements, some details of requirement from the renewable energy sources also spelled out. So, but broadly, this can be divided into a couple of grid connection requirements. These are the major ones, which are generally known as active power or frequency regulation requirement, reactive power or voltage control, fault right through capability, and the scheduling, dispatch, forecasting, or power quality. Some of these issues can be considered in the grid codes. Similarly, we are also able to see that other issues for a large-scale grid integration of the renewable energy sources is about the evacuation of the energy also, which requires augmentation of our power infrastructure, especially the power transmission line, distribution system also, because most of the smaller scale renewable energy sources like small wind farm and this farm, they are generally connected at a 11 kV or 33 kV system. So augmenting a power transmission and distribution line also, or and if required, a new line also. So that issues are a bit a longer term investment issue, but that requires, otherwise there are the cases where a higher generation of the wind energy are generally curtailed, especially in Tamil Nadu, where the evacuation of the energy, considering the congestion, becomes an issue. Then another problem is about the connectivity is a interconnection point, also known as PCC, point of common coupling, PCC, where this is also being debated that the infrastructure up to the PCC is being generally developed and maintained by the renewable energy source, but after that it is by the state utility. Then the question here is that where should be the interconnection point? Fine. So up to what infrastructure? So there different states are having different, you can say, PCC points, the definition of the PCC point. So in overall country, it is required that there should be a common understanding between the point of common coupling, so that it becomes a important generalization of the policies, so that the different wind and solar farm owners are having a more comfortable and convenient situation. Is this fine? Okay, if you are having any concerns, questions, then you can please raise. Now let's see what is a wind power. We will be discussing more about the wind power while discussing about the grid connection issue. We are able to see when a wind flows, it strikes to turbine, which is having the blades, then it is rotating and which generates a torque, and this generator will be able to convert electricity from this mechanical energy, being kinetic energy to mechanical energy to the electrical power. So these expressions are given. The below expression, which is giving a for a power, is kinetic energy by T is half rho A V cube. This rho is the fluid density. In this case, it is a moving wind. A is the area which is swept by the rotor blades, and V, capital V, stands for the velocity of the wind. So from this expression, we can easily see that the velocity of the wind is a very, very important factor, because V cube is coming. So a windy site it becomes very important, and then it suddenly gives, due to its expression V cube, a higher energy generation as compared to another side. So this is how it trade-offs are there. We are having estimated wind potential of around more than 100 gigawatt. These are the bit old data by the CWAT, but now a couple of new sites are also being identified with a higher hub height of a wind turbines. This is, I think, we have already discussed. Now coming, there are many schematics are there for a wind energy conversion systems. A left hand side, you can see a typical configurations is given, in which a wind turbine is there. Wind turbine can have different configurations, whether it is a horizontal hub or vertical axis is there, or number of blades are also different, but generally 3-blade system is being used. Then gearbox is there, which may be optional based on which type of generator is being used. Then a generator, whether it is a double-fed induction generator, which is most popular, synchronous generator or permanent magnet synchronous generator, there are, or squirrel cage induction generator, there are different type of generator configurations are there. Then many times a power converters are also being used, then a power transformer to make sure that the power levels are being matched, and then it is connected to the grid. So this is a typical configuration, and good number of schemes are available for wind energy conversion scheme. Let's see, this is one of the scheme known as fixed speed generator that was very popular couple of decades ago, in which a squirrel cage induction generator is there, and which is directly connected to the grid, and this 3-blade system was there, is having a issue of reactive power requirement. As we are aware of, induction machine requires reactive power, and which is being fed by either by a grid or by a switchable capacitor bank. But this configuration was very economic, very robust, a very you can say maintenance free, but the generation was being limited, power quality was having an issue. Then there were different type of schemes are here, which is known as variable speed converter interface system. The topmost scheme is there, in which a wound rotor induction generator is there, in which the speed is being varied by using a variable resistance in the rotor side, and it is also directly connected. But the variable speed system was able to provide more energy generation from the same setup. We will be going to see that why the variable speed system is able to generate more energy in a coming few slides. The middle scheme is based on squirrel cage induction generator or synchronous generator or permanent magnet synchronous generator, in which the stator is connected with a AC to AC system, by which the variable speed is being achieved by using control of this power electronic converters. And once again, there are certain benefits are there due to the variable speed system. But in this case, you can see that complete power is being processed, which is generated by the generator through the power electronic system. And right hand side converter, which is able to generate a AC power, which is as per the requirement of the grid. And by control of this power electronic equipment, we can have a control of active and reactive power also. This we will be going to discuss in coming few slides. The third most popular scheme, which is given as a below, which is known as double-fed induction generator. In this case, you can see the power electronic converters are placed in the rotor circuit. And due to that, there is a very big advantage is there. The rating of this converter being connected to the rotor side with a limited speed variable or speed margin is there. The cost of this overall scheme becomes very, very less. So there is a advantage in the terms of economy. A power quality can also be controlled very well. Controllability is also very high. So this scheme becomes very popular. Good number of DFIG overall in the world is being installed whenever we are talking about installation. But as the penetration level is increasing, fault right through capability also becomes a issue. And slowly the synchronous generator, conventional synchronous generator with a converters in the stator takes the a edge over the DFIG scheme just due to the better fault right through capability and to maintain the stability. So slowly the trend is changing to the synchronous generator with a full converter in the stator side. Fine. If you are having any question or concern till now, you may please raise, or you may write in the chat box also. Now let's see this generator system for the wind turbines. We have seen, then we are also able to see a variable speed system is being introduced. Now the question here is that why we want a variable speed system? Then some of the researchers have identified that by having same height of a generator system, hub height, there could be an increase in power generation for the same condition, same height, up to 30% also. So why it is possible? We can understand this by using a couple of expressions. This first expression is given here, power from a wind turbine rotor, which is given as Cp into half rho A P cube. In this case, only Cp is the new factor, which is known as power coefficient. The theoretical limit of this power coefficient is generally 59%. So it means the power which is coming from a wind turbine is multiplied by a Cp, which is only 59%. So why this is happening? And this is also known as Betz limit. You may have learned this Betz limit somewhere in some course of hydraulics engineering in your BTech time, if you remember. It's very interesting, a very small derivation. You can also see how it is coming and why it is coming. So why this Betz limit is coming? Let's see another expression known as lambda, which is given as R omega by B omega. What is this? This is known as tip speed ratio. Tip speed or ratio. What is this tip speed ratio? The tip speed ratio is a ratio of tip of a moving blade divided by the velocity of the wind. So in this, R omega by V omega is known as tip speed ratio. So if we plot the power coefficient with reference to this tip speed ratio, then the right hand side top figure you will be able to see, which is a curve you can see. Now you can see for a particular tip speed ratio, the power coefficient is maximum. In this case, this is a actual data. So you can see the theoretical limit is 59%, but in this case, it is only coming out 39% only. So this is a actual mechanical system is there, which is providing. So now we can see that if we are able to play with a rotational speed of a wind turbine for a given wind speed, we can maintain the maximum power of coefficient. It means our system should be variable speed system. Our system should be variable speed system so that we will be able to always change the rotational speed to maintain this lambda for a particular value. And it depends on which type of wind turbine we have considered. So that's why we can say that a variable speed system will be allowing us to continuously vary the tip speed ratio or the tip speed of a wind turbine, so that with a change in the wind speed, we will be always working at a maximum point of this curve. So similarly, when these curves are being translated in the terms of generated power versus the wind turbine speed, a below figure is there. The below figures, let me say how it is being drawn. The x-axis is a turbine speed referred to the generator side in RPM, and the y-axis is the power in kilowatt of a generator. So this depends on mechanical turbine characteristics. Right? There are different curves are being plotted, and this is plotted for a different wind speeds. So wind speed from 12 meter per second, wind speed of 11 meter per second, 10, 9, 8, 7, 9. So now you can see, if we want to always maximum of these curve for a given wind speed, then we always need to change the speed of a turbine or the speed of a generator in this case, which is being referred. So it means we always want to work on the maximum operating point, and this algorithm which allows to follow the maximum point is known as MPPT, maximum power point tracking. There are good number of algorithms are there. Let's understand this curve. So if you can see a characteristics of a wind speed of a 10 meter per second, we are able to see this maximum point is coming somewhere around 1500 RPM. Let suddenly, if your wind speed is changing to the 8 meter per second, then we can see the maximum point is coming somewhere at 1100 RPM. So it means if the wind speed is changing from 10 meter per second to 8 meter per second, we should be changing the rotational speed of a turbine from 1500 RPM to around 1100 RPM, so that we are always capturing the maximum power which is available in the wind. So this is what a basic nutshell reason to make a variable speed system to operate on maximum power point of a turbine characteristics. Is this clear? Is there any query in this? Then please let me know. So there is one question or one query is there. Let's read. This query is saying a power system can have more than one wind farm with different capacity. So what should be profile of grid code? Means it should be same for all wind farm or different for each wind farm. So let understand this, that when we are talking about the grid codes, we are talking about whoever is connecting to the grid. Fine. Electricity Act gives an open access which allows us to be connected to the grid or get injecting the power and can take the power. But it also says that we need to maintain a grid discipline and we maintain some minimum requirement. So that's why grid codes are applicable to all, whether it is a X type of wind farm based on particular configuration or it is a Y. So this is a requirement for every type of wind turbine technology. Fine. I hope this address your query. Then another question is, how can we contribute for supporting ancillary services as prosumer using RES? So when we are talking about ancillary services, it means like providing a, I hope it is what you meant is that how we can provide the reactive power to the grid, or how we can provide the support to the grid and maintaining the frequency. If you are talking about this, then let me address in coming few slides. So that will be coming here. So this is overall known as grid code. Fine. So that will just come in few slides. Right. So I hope this concept of variable speed system may also be clear. Then we can see that different grid codes are being given by different countries and we are continuously improving also. Broadly, these are the 4 grid codes that we will be going to discuss. So grid codes are there. Let me just have a grid code known as active power control. What is the meaning of active power control? The meaning of active power control is that we will be able to control the active power output of a wind turbine. And if a frequency in this curve, you can see this is from the Indian Electricity Grid Code. If the frequency is more than the 50 Hertz, so slowly a reduction in is expected from the solar farm or wind farm, and after 51.5 the output should be 0. So this capability with the wind energy conversion system or wind farm should be there. With other than that, a adjustable upper limit is also be available with the utility, or the control should be available. Then ramping control means that suddenly you are having a wind is blowing, then but you can't connect the output of the generation in the same fashion. A ramp is also prescribed by the Indian Electricity Grid Code. Fast down regulation means if some abnormal condition is there, how fast you can disconnect from the grid to maintain this stability. Another one is automatic frequency control, which controls that if a wind farm and solar farm can participate in the frequency maintenance. It means active power can be injected, active power can be reduced also. Injection becomes a difficult because we are aware of, we are already working on maximum power point tracking. So injection becomes very difficult for us because we are already working on a maximum power which is available to us. In this case, a energy storage system will be helpful with a wind farm so that a additional power injection can be there if a frequency control is also exercised. Reduction is very much possible for the such sources. Some of the researchers are proposing that instead of working on MPPT, based on whatever the frequency band you are working on, a same reduction can be done. So it means if you are working on a MPPT, then this can be worked with that MPPT minus certain delta X, so that you are continuously losing a available kinetic energy, available power from the wind turbines, wind energy conversion system, but it gives a flexibility that you can easily inject a additional amount of energy because you are working less than the MPPT, so that to participate in the automatic frequency control. So this is what bit details are there. I will skip all this. Here you can see a references there, technical standards of connectivity to the grid, regulation amended in 2019 for 10 megawatt and more there. Another one is about to provide a reactive power or voltage control. So in this case, to maintain the zero reactive power exchange with the grid, so such capability should be available, and if it is required, a reactive power should be injected as similar to the conventional synchronous machine system. The below figure, you can see it is for the voltage control requirement, in which a red line is there, and you can see which is the having a requirement of voltage versus additional reactive power. This is X and Y axis. So it means if a 50% of voltage dip is there, the 1 per unit of additional reactive power is required. So such type of system in which reactive power should be injected from the wind farm to the grid, that can be achieved by having a power electronic converters by having higher rating, and in this case this devices will be able to inject a reactive power, similarly for a solar farm also. So this reactive power can be achieved, such type of characteristics can be achieved. Fine. Then another requirement, let me skip this one. Then coming to a very important task is known as fault right through. In this case, the meaning is that whenever the abnormal condition or fault is happening, your wind farm and solar farm remain connected to the grid and will be able to inject power as per the requirement. So this is a curve from a German grid code, which say that red thick line is the thick line, and above that the operation should be there. It means the 0 to 150 millisecond, if a voltage is there of a distribution or transmission line where the wind farm is connected, if the voltage is 0 also up to 150 millisecond, the wind farm should remain connected to the grid and should inject to the power. So this is a very difficult and important requirement as a grid code with the wind farm. So no tripping is also required. A short-term tripping is required if wind farm are not able to sustain. And beyond that curve and this red thick line, a short-term interruption is possible, and then stepwise tripping can also be there. We can discuss very briefly when we are talking about doubly-fed induction generator how to meet this requirement. So in India, we are not very strict. We are saying up to 15% of per unit voltage is there, then up to 300 milliseconds it should remain connected. If it is less than the 15% of the voltage where the wind farm is connected, then system can be tripped. And it also depends on what voltage level the wind farm is connected. And high voltage protection is also there, in which if a grid voltage is getting beyond 1.3 per unit, then a instantaneous trip is allowed. Otherwise, between 1.3 to 1.10, a time limit is there. Afterwards, a tripping can also be done. This is known as HVRT or high voltage ride through. Then we are also worried about the power quality. Then a IEC standard is generally applicable, where the power quality is also need to be maintained as per this IEC standard. So in overall, we need to see that at a point of common coupling, the grid codes are applicable. So either each individual wind energy conversion system can be augmented to meet all these requirements, especially like reactive power or active power. Then if it is not, then can we provide some additional add-on equipment, generally known as capacitor bank, SVC, static compensator, or energy storage in the terms of battery or a diesel generator, so that these requirements can be met at a point of common coupling, so that a grid compliance can be achieved. So this is what the major grid codes are there. Fine. Now let's see what is a popular scheme of doubly fed induction generator and how it will be able to achieve the meanwhile we are having one question. This question is which is saying, what could be the adverse effect of a large wind farm on a voltage stability? So to understand this, let's see this particular diagram. You are having a large wind farm connected to a grid which is connected at a point of common coupling by having some transformer. If the line of this feeder, which is connecting up to the point of common coupling, is very long, then we are aware of, and especially when it is a offshore wind turbines, means the wind turbines are in a sea, and then a large power cable is there, then we are able to see that a charging issue is there, and at that time voltage stability is a important factor due to that charging current issue of a power cable. So that becomes a very important consideration. Few of the large wind farm are using a HVDC concept for the evacuation of the power in such cases. So that is obviously a big concern in the terms of voltage stability, when the distance from the wind farm to the main grid is having a longer line. In that cases, it is the issue. Fine. Now let's give few minutes to, I hope this address the concerns raised. Otherwise, you may please type once again, then we can once again look in more detail if required. Now, when we are talking about doubly fed induction generator, this scheme is there. Let me explain this scheme and then see how it can be able to make sure that it is able to meet the grid connection requirement. A doubly fed induction generator is shown here. The rotor side, you can see a rotor side converter is connected, which is AC to then DC, then the coupling DC link is there. In DC link, there is a chopper is also connected, and then the line side converter is also there, known as sometimes grid side converter also. So this converter is converting DC power into AC power and then connected to the grid through a transformer. Fine. And this stator is directly connected to the power line. So this is how our doubly fed induction generator is there. The name doubly fed is coming from the doubly fed is coming from that a concept or a view that in this case this induction generator can be fed from rotor side as well as from the stator side. This is why a name doubly fed is there. The power in the rotor circuit can flow from this rotor to the rotor side converter, DC link, line side converter, and can grid. And generally this situation is known as super synchronous mode. During the sub-synchronous mode, the power will be coming from the grid to the line side converter, to DC link, to rotor side converter, and feeding into the grid. So this is how the power is flowing. By controlling this rotor side converter, the main objective of rotor side converter is to inject a appropriate voltage in the rotor of this doubly fed induction generator, so that speed can be controlled, so that the output power at the stator, which is known as stator active and reactive power, can be controlled. So by controlling the rotor side converter voltage, which is injected into the rotor, the speed as well as the power output from the stator can be controlled. This rotor side converter can also inject a reactive power for the utilization of the doubly fed induction generator. And by utilizing this concept, the overall this induction generator becomes overall this induction generator becomes a reactive power supplier also, because the whatever reactive power is being fed from this rotor side converter, it goes to the air gap for the requirement of the induction machine, and if it is required based on certain operating condition, the same reactive power can be enhanced, and then it will start flowing from the stator towards the grid. So it means reactive power can be given to the grid if it is required, but the rotor side converter control should be operated. So it means overall rotor side converter is just interested in maintaining the active and reactive power of the stator, which is connected to the grid directly. So during this process, this rotor side converter is taking power from this DC link, or it is injecting power to the DC link. To maintain this DC link voltage, the responsibility lies on the line side or grid side converter. So whenever the grid side converter sees that there is a dip in the DC link voltage, it will take the power from the grid and it will inject here. And if the rotor side converter is taking extra power from the rotor side while controlling the speed of a doubly-fed induction generator during super synchronous speed operation, then this extra DC link power, DC power, is being fed from this grid side converter to the grid back. So this is how the grid side converter is having responsibility of making or making this DC link converter, DC link voltage. The grid side converter is also having a additional responsibility based on the requirement to act as a static compensator and to inject a reactive power if it is required to the grid. So this LSC can also become a static compensator. So this is a additional functionality of this LSC. So this is how we can see that reactive power ancillary services can be met. But when we talk about active power, it depends on the whatever the power is available in the wind, and the rotor side converter will identify basically overall this how this algorithm is working. It is working like that. Based on the wind speed and the turbine characteristics, a maximum operating point is being identified, and it is saved in a lookup table in the control. And from this lookup table, it can be identified for a given MPPT point what could be the corresponding speed, and that speed is then acting as a speed reference for this doubly-fed induction generator, and then which is being converted that what voltage should be injected. So this is how we are able to find out. We are finding out what is a wind speed. From this wind speed, from a given characteristics, we can find out what is a maximum power can be achievable based on this maximum power and the corresponding rotational speed. That rotational speed becomes a reference point. From that, some controller will act as a actual speed, reference speed. The error is being calculated. This error is now converted into what should be the voltage being injected into the grid or into the rotor side of the doubly-fed induction generator. So this is how the overall scheme is working. The reactive power set point is being directly based on how much reactive power is required by the grid, how much reactive power is required by the DFIG, and overall reactive power set point is given by the rotor side converter. So this is how working. At last, we can discuss one more point here, which is that what will happen during a fault condition. Now we can see whenever fault is happening to the grid side at the point of common coupling, voltage is reducing. Voltage sag could also be there. Voltage, different type of faults can also be there. If the voltage is reducing, the current in this whole circuit is going to be increasing. If the current is increasing in this circuit, then what can happen? This power electronics converters can be damaged. So to address this issue, two provisions are being provided. One provision is known as chopper, another one is known as crowbar. Let's see. The crowbar is going to act first. What is this crowbar? Crowbar is just a set of resistances which is controlled by some semiconductor devices. So what will happen? We'll see what will happen to the crowbar. Before that, let's see how the chopper is going to work. Chopper is also going to have a resistances which can dissipate power with the help of some controlling semiconductor devices. Whenever the power in this whole rotor circuit is increasing, chopper becomes activated. Some power is getting dissipated in this chopper so that the DC link voltage becomes remain stable, and the extra power which is flowing in this circuit is dissipated here. Some of the researchers are saying that a severe fault, zero voltage at the grid, can also be overcome by operational and the design of this chopper. But some of the researchers are saying that if let a chopper is not able to overcome such type of power dissipation where a long fault are there with a higher energy which is flowing here, then crowbar will come into the picture. When the crowbar is coming into the picture, it will provide the resistances in this. If this is a three-phase double-fed induction machine, the three-phase resistances are there, and which will short circuit this rotor of the double-fed induction machine. And in this case, DFIG is going to act as a squirrel cage induction generator, and there are resistances are in the rotor body which is able to dissipate the extra energy which is coming here. So this is how the fault can be ride through. But in this case, we can see that the double-fed induction generator becomes a squirrel cage induction generator. Rotor circuit is now get disconnected. So during that time, the reactive power can be provided by this grid side converter, as we have discussed earlier. So it means by operation of this chopper, crowbar, and grid side converter, fault can be ride through. Reactive power exchange during that time can be achievable. So when this crowbar is operating, a short-term interruption is known. That's why, if you remember, we have discussed this curve known as fault ride through, that a possible short-term interruption is there, which is here. It is shown here. So this condition, which is given by second condition, 2 with a round, this is known as short-term interruption. So that type of condition is allowed by operation of the crowbar, in a double-fed generator. So with this, I would like to stop here. I think my time is also getting over, and overall we have discussed something known as grid codes, active power, voltage control, or known as reactive power, fault ride through capability. Also, these are the three major we have discussed. Then we are also able to see that how a typical double-fed induction generator scheme, which is the most popular wind energy conversion scheme, is able to meet the active power, reactive power, and fault ride through capability. So with this, I would like to stop here. If you are having any question, then please let me know.
Thank you so much, sir.
And
It
if
was
the time is
very
there,
nice
I can,
of you to explain in such details.
Yeah. If time is there, I can cover something more also, but it depends on your schedule. Hello.
Hello. Sir, can you hear me? This is Atul.
Yeah, I am able to hear. It seems Diksha got disconnected.
Yeah, sir. I think there is some issue with his with the network connection. So, sir,
Yes.
if you would like, we can have like 5 to 10 more minutes from your side.
Is this allowed? Then let me. If you have time, then I can discuss something on renewable energy certificate if the time permits.
Yes, sir. 5 to 10 more minutes we can have, sir.
Okay. The 10 minutes are there. Let me just introduce that.
Okay, sir. Okay, sir.
So are you able to see the screen now?
Yes, sir. Your screen is visible.
it is in full screen mode.
Yes, sir.
Okay, so let me just skip all this. These are some technical issues. Now, when we are coming about the high capital energy cost also, and to meet the RPO requirements, a renewable energy certificate is one of the mechanism. Let me just introduce briefly that certificate mechanism. So this renewable energy certificate mechanism is given in 2010. What it is saying that renewable energy generation can be fed into the grid, then how to remunerate them. One option is that let's give them the price which is known as preferential tariff. So whoever is having a bilateral contract with the wind farm or solar farm, they can have a preferential tariff which is decided by the State Electricity Regulatory Commission, and they are getting remuneration. So this is a very, you can say, well-established system. But the issue here is that let's take an example of Delhi or Haryana. They are landlocked system. They are having very limited wind and solar potential with them. How they will be able to meet their renewable RPO requirements? So that a REC mechanism is being introduced. What this REC mechanism is doing, REC mechanism, which is a parallel mechanism to the preferential tariff, which is saying that let's divide the renewable energy generated from the from a wind or solar into two parts. Fine. Let me show this particular slide. So existing mechanism is saying that upper schematic renewable energy is distributed company, a tariff known as preferential tariff, which is by the regulatory commission. Now coming to the below figure, the renewable energy is now divided into two parts. One is simple electricity, and nobody bothers whether it's electricity from coal, thermal, hydro, and whatever. They will get a price of this electricity. And second component is known as attribute of this electricity, which is that from where it is being generated. In this, it is generated from a renewable energy. So then a certificate is being issued for this generation, which is known as renewable energy certificate. So now this renewable energy is remunerated by two. One is known as electricity, another one is known as certificate. What is the price we are paying to the electricity? The electricity is being remunerated. The electricity component of this renewable energy is remunerated based on either a bilateral agreement or it is a average purchase or average power purchase cost of host utility in the as per the previous financial year. How they are finding out this average power purchase cost? They are just finding out how much power they have purchased divided by the overall unit they have purchased. This is how a average power purchase is being calculated. So the electricity component of this renewable energy is enumerated based on average power purchase cost, and which will be obviously less than the preferential tariff or the minimum requirement of a renewable energy source, because they are going to be in a loss, because generally the hydro or the thermal is going to be cheaper than, and overall this average power purchase is also going to be cheaper. So from there they will get an extra component. They will get an extra component from this renewable energy certificate mechanism. How to find out the price of this certificate? This price of this certificate can be found out in a power exchange. So this is how the certificate can be there. For this certificate, the once again this slide is there. In this certificate, you can see right hand side REC component or renewable component attribute is in a paper form, can be discovered. The price can be discovered in the market, and there is a range of the prices there known as upper price and the floor price. So their price is going to be variable and depends on how much these certificates are in demand. So it's something like a market or share market. Fine. Left hand side you can see typical power purchase cost of different states are given. Right hand side you can see typical price of per megawatt hour is also given. It means 3.9 for non-solar up to the 1.5. So 1.5 to 3.9 rupees plus average power purchase cost will be given. So this is known as renewable energy certificate mechanism, and this price is ranging between them. And to find out what would be the floor price and forbearance price or upper price, this regulation, REC regulation, has enumerated the whole process. We will not be going into the more detail in that mechanism, that how this price is being calculated. It requires some historical data. I'm having some details, but we'll not be able to go into more detail. The historical data is required, then it is being arranged in certain fashion, then a minimum or maximum is being calculated like that. So this is how a price is can be find out. So with this, now let me stop here. If you are having any concern and question also in this REC mechanism, you may please ask. Hello.
Yes, sir, you're audible.
So with this, I would like to stop here. If you are having any question, then please let me know. Or
Hello, sir. Am I audible?
yes.
Yes, sir. Thank you so much for such a nice presentation, sir. We understood it in good details because of the lucid way you explained it. And it was an honor to have you here with us. And as a token of our appreciation, we would like to share this online felicitation from IEEE for you. And we would like to have you here with us physically on campus for future events, sir. Jitendra, could you please share on the screen? So kindly accept this token of appreciation.
Yes, thank you. Thank you very much. It is always a pleasure to be having some interaction with IIT Kanpur. Thank you.
Thank you so much, sir. With this, we would like to conclude the morning session of day 5 of Para. And we hope to connect with all of you for the evening session, where we'll be having a panel discussion from 6 to 7 p.m. on towards sustainable and resilient power system. We have as our panelists Professor S.N. Singh, Professor Saket Chakrabarti, Mr. Abby Joseph, and Dr. Swati Batula would be moderating the session. We hope to connect with all of our evening session. So have a nice day, everyone. Thank you.